Hello, it's me again, and we are going to cover chapter 2 today. So, course textbook, I follow the textbook, but the lecture notes are written by me and they complement the textbook. And here are chapter 2, Finite Automata. And chapter 2 has three big pieces. Slide set 1, Deterministic Finite Automata, DFA. Part 2, Non-Deterministic Finite Automata. And we will prove the equivalency of those two creatures, which are called finite automata, deterministic and non-deterministic. And the next set of the next part is finite automata and regular expressions. So we connect the automata with regular languages and prove different things, and we show how it connects, so what does it mean. And then we will examine using all the automata and all the language and theory we developed to examine how we can prove or not prove that languages are not regular. And then the next set of slides is the state minimalization, and so that's sort of another subject. So, deterministic finite automata. What it is? Deterministic finite automata. Here is a simple computational model. If you want to imagine how it looks like, we have the input tape and with squares, and we have a reading head which moves from one position to the other. And in the reading head, we have a finite control. And of course, input tape is divided in squares and one symbol in the square. And now an input string is always put, or input string, it means our word, is always put at the beginning of the tape. And now the operation is governed by the black box, which is called finite control. And it can be in any specific time in one of the finite numbers of states. So that's why here you have a finite number of states. And reading head is a movable reading head, can sense which symbol is written in any position on the input tape and moves one square to the right. So here it is in the state Q2, senses A, and then if it reads A, will move one square and go to a new state. So, and now we have certain assumptions that there is no output at all. Deterministic finite automata indicates whether the input is acceptable or not acceptable. And deterministic finite automata is language recognition device. It means it will tell if the word is accepted or not. And now the operations. Initially, the reading head is placed on the leftmost square, the beginning of the tape. Finite control is set in initial state. After reading on input symbol, the reading head moves one square to the right and enters a new state, and the process is repeated and ends when the reading head reaches the end of the tape, because our word is a finite word. It can be so, and it reads one letter at a time, so it will always end, because when it reaches the end of the word. And operations initially, okay, we did it. So the general rules of operation are: at regular intervals, deterministic finite automata reads only one symbol at the time from the input tape and enters a new state, and the move depends only on the current state and the symbol just read. It means is described by a certain function. So now we want to, and then the process stops. When the process stops, DFA indicates its approval or disapproval of the string by the means of final state, because it always stops, because when it reaches the end of the word, it always stops, but we have to know if automata accepts or not. So the approval is indicated by the means of the final state. So we'll have certain states which we'll call final states. And if the process stops when automata is in the final state, the word is accepted. And if it stops, because always stops, which is not in the final state, the string is not accepted. So this is how, and now we want to, from that description, we want to build a mathematical model of that. And you can see already that, like for example here, the move depends only on the current state and the symbol. So you have a current state and a symbol, and then it moves. So the move depends only, so the move has to be described by a certain function. And we have informal definition that language is accepted by deterministic finite automata is equal to the set of strings accepted by it. And we already know what does it mean. What does it mean that the string is accepted, that automata read the word and stop it in being in the final states. So what we need finite set of states. We need alphabet, because we talk about languages. We need initial states, because we start computation in the initial state. And we need a final state or final states. So that would be we need to have all those components. And the description of the move is at regular intervals reads only one symbol and enters new states. So the move of DFA depends only on the current state that the symbol just read. It means what? That we need a function which takes a state, reads a symbol, and goes to the other state. The move, this is the move, must be a function. So here is our automata, and let's route it here, because that's what we will have now. M is 5 pieces, which is quintuple. K, sigma, delta, S, F. So this is our automata, where K is finite set of states. Sigma is alphabet. S, this is here in K, as we said, is initial state. And F is a subset of states, is set because we can have more than one final state, and we have only one initial state, set of final states. And the move is our function. Delta is a function which takes a state and a word and returns another state. in a state Q, reads some sigma, and enters into another state. And this is called a transition function. It's called transition function. And of course, we use different symbols, so we assume that K and the states are disjoint sets. We want to have the fact that we say K and S, but we have to say that we want to use the different symbol for the different states. So now when you look at this, let's see, what does it mean? We have this finite set of states. First, finite set can be empty. So, but we know that S is in K, so we know that K is non-empty. So you can see that now we know that K is non-empty because S is in K. So if you say finite set, it doesn't mean that it's non-empty. If I say K can be empty, but it's unempty because S is in K. We assume that S is in K. Sigma is an alphabet. What is alphabet? Alphabet is any finite state, so sigma can be empty. So that is to remember that we have a case to consider. If we say alphabet and sigma is an alphabet, it can be empty. And F is set of final states. Again, empty set is a subset of any set. I didn't say that it's non-empty. So again, we can, if we want to may be empty, so we will have, if we want unempty, we will say F non-empty, and the same we have to say sigma non-empty if we want sigma to be non-empty, because it can be empty, and this is a transition function. So this is things to remember about the definition. And so as I say, if you have delta, delta is a function between K and sigma. It means delta in a state Q reads sigma in sigma and goes to the state Q prime. And now we have an important notion, which is a notion of configuration. So configuration, because we want to describe the move of automata, right? This whole control reads, goes to another state, moves along the word. So we want to describe what is the move of, is given by the transition function, but we want to describe it, the move of automata from one state to the other along the tape. So we introduce the notion of configuration. Configuration and is any tuple in K times sigma star. So what does it mean? If you want to imagine, what does it mean that this tuple is the configuration? We have certain word, B, A, B, whatever. I said sigma is 2 elements. And now we have our finite control is here and is in state Q. And for example, if you have image like that, this is a part of red, part of the word, looks at B, and that part is unread. So the configuration here, if you say that this is state Q2, so the configuration here would be you are in a state Q2, and and you look at B, A, B. It's different than here. So it means that you are here, you are in state Q, you look at B, with a red part is the whole B, A, B. And it depends on the move, the configuration are always a state, and the word, which is unread part, and before is the red part. And now we move, the move, so in general, the set of configuration is K sigma star. You have all possible configuration. We define the move of the automata, and this is a relation between configurations. So the move is between two configuration. It means the move is between configuration W to Q prime W prime. So that's why you have, it's a binary relation. That's why you have a square here. And we say, for short, that we say that given an automata, we have that one configuration, sigma W, that means it looks, automata looks at sigma, that is unread part, the whole thing is unread, in move to another state Q prime, and you read delta. So now an unread part is the whole W, if and only if delta, because M is defined by this delta, delta of Q, this Q, sigma is Q prime. So that delta tells how automata moves between two configurations. So for example, when you let's do, and then you use that relation to move from one configuration to the other, and then the relation to another and another. And the whole move is called a computation. For example, if you have S, A, B, you move into Q, A, B. I want to have the same. You move, our automata moves to S, B, and moves to Q, E. What does it mean? That's end of the word. So what does it mean? That here, if you have the delta in our automata in a state S, which is initial, looks at the word, sorry, S reads A, goes to state Q. So this is this move. Now, that says that in a state Q, so it means delta in the state Q reads A and goes to the state S. And here means that delta in a state S reads, that's it, right? Because that stops, because the whole thing, this is a stop, because the whole word had been read. So once you have a computation, you can guess what was the delta which that automata produced that computation. And so you write that m is given by your delta, and the sequence of configuration is called a computation, and computation is from initial states to some state q, and then E means that the automata stopped because the whole word was written. And we say that, so you have another example. And now, and we say that the word is accepted by M if and only if the computation starts in S when M is initial state. That's true because it started. The whole word has been read. It means you have E here. That denotes that we finish reading the word, and that we finish in a final state. So the word AAB would be accepted if this Q state is in a final state. Otherwise, it's not accepted. And the sequence, the general definition, the sequence of configuration is a computation of the length n, if and only if the first is initial state. You have in between, you have transition function, and you go from one to the other by the transition. So it doesn't mean we don't know, it stops some, it's just the computation of the length n from W1 to Wn, whatever is W1. And the work's accepted by M if there is a computation such that the beginning is S, word, the last one is the word, and Qn is in a final state. So Qn is Q in the final state. We say that the word is accepted if you have such a sequence of configuration, that or such a computation that it starts with in initial state with W and ends in final state. So we can say that W is accepted by automata if there is a computation which starts with initial states, read with W, and that means that the W was read by automata and Q is in F, otherwise it's rejected. And that is in plain words. And the language, what is the language? We say the language is accepted by automata if is the set of all words in sigma star, then W is accepted by the automata. It means it's accepted. There is a computation which starts with W, and E means that W had been read, and then Q is in a final state. So you say for some final state, it means there is Q when you Q which we finish reading is a final state. And here is a little automata, and you have different ways of what does it mean to define automata. It means that you say you have two states. You have to give sigma. Sigma is AB. You have to design which of those states is initial states, and which set of states is a final set of states. Here I say that there's only one final state, which is Q0. So I say F is set which has only Q0, and you have to give transition function. And transition function, you can give transition function in different ways. So this is nice to write this at a table. You can say that, for example, is a final set transition function is K times sigma into K. So here delta would be a function in this case between Q0, Q1 times AB is two elements into Q0, Q1. So it means I can write, so you have states Q, you have sigma in sigma, and you write the delta of q sigma, and I say that q0 a, I assign q0, q0 b, I assign q1, q1 a, and q1 b, I have to assign certain value. So here I assign q1, and here I assign q0. Delta, you see here, because delta is a function, it means the domain is this Cartesian product. So this is the whole elements of Cartesian product, and so the delta is properly defined. And now we can ask, I define an automata, and also I can say, I have to say, what is a finite? I said, oh, my q0 is a final state, and I say that S is also q0. So that also says that the final state can be also initial state. I didn't say that the set of final sets at initial state is non-empty. And now we have determined, for example, if the word belongs to the language or not. And now, very easy, you start the initial state, and delta, we define delta of q0a reads a is q0, so go to the state q0 reading a, and I have the unread part is BAB. And now here in q1 and q0, I look at B, delta goes to q1, so I have q1, and now in q1 reading A goes to q1, and so on, and in q0 reading B, by definition q0b was q1, so I read the whole word, and this is the end of computation, and q1 is not in F, which was only the set q0, so we prove that it's not that word is not in the language. And you have other. Now, okay, so that's how we define the computation and define the transition relation. Now we use a new notion. So that was our transition relation. Transition between relation. And now we define the computation with the notion of transition relation and reflexive transitive closure of that relation. We go back and we say that the language is the set of all words that from SV you go by reflexive transitive closure of our relation M. Why? Because we proved that transitive if you have transitive reflexive closure of any relation represents a path, which is exactly the computation. So this is a nice, and if you write SW, reflexive transitive closure represents a computation from here by the transitions 1, 1, 1, 1, 1 until you get here. So that's why we write in a, and we will be writing, instead of spilling all the time those computations, we know that that reflexive transitive closure of any relation represents a path from this to that. It means represents the computation from SW to QE. And we have different examples. Now, so now we will have language is the set of W in sigma star. that as W, there is a computation to QE. It means the whole W was read, where Q is in a final state, or for Q in a final state. So it means there is a path between that configuration to that. A path is that computation, step-by-step computation. So as I said at the beginning, what does it mean to define an automata? It means to define or to give an example of automata means you have to specify the components, right? So for example, we have sigma, which is 2 elements. K has 2 elements. Define 3 automata. Define an automaton such that language is empty. How many of automata can be defined? So I gave you 3. What does it mean? I already have this. I said I have to say which is my initial state and which is the final. And here's I have to define the delta. The next, here I change f so that is a different automaton. And I wrote some delta. And remember, always when you define, the delta has to be a full function. And here's another one, because I change the delta, I change here. So there are 3 different. And what does it mean? Defined automaton such that the language is empty. Very obvious way to define is when you put the set of f empty, so the language should be empty because it will never finish in a final state. So how many automaton? You can say if you have, for example, 2 elements and here 2 elements. So for example, first they have different function. So how many delta you would have between k, 2 element k, and 2 element sigma would be 2 to the 4 possible choices of delta. Of course, they can also different on the choice of final states. So there are as many final states of 2 element set as all possible subset. So you have 2 possible choices, and then you combine all the choices, and you can say, you can compute how many possible automatas you can define with those over sigma a, b, and with 2 states. And there's different challenges. So now you see, now we introduce the important notion. It means we defined a state diagram, which is like a graphical representation of all those really on the function of the transition function. So we need, we write, this means state, and that means initial state. So it means that this state is initial state. If we put dot inside, or if you put bigger, you can put, we say that this is final state. And we write, if you have state Q1 and you have state Q2, and we write arrow between Q1 and Q2, and sigma is in sigma, that represents the delta of Q1 sigma equal Q2. So now we can draw a picture of the automata using those pieces. And of course, if you want a loop, and here is your state Q, so it means that delta of Q sigma equals Q, and also that means that this state Q is initial state of automata. And now we can draw a pictures instead of writing those tables. Here is an automata, and we can ask, what does it list all the components? It means you know that initial state is Q0. Here, initial state is Q0, which Q0 is also in a final state. And delta between Q0 to Q1, delta of Q0A equal Q1. And here you have loops, and you can describe L as regular expression. And here you can see, you can read it, that delta between Q0A is Q1, Q0A is Q1, delta of Q0B is Q2, Q0B is Q2. So you have a table for delta, and of course you know that Q0 is initial, F is, because I put dot into those two states, so F is Q0, Q1, and the transition function is given by such a table. And now the language is all words you can read starting and Q0 and ending in the final state. So when you look at this, you can see what's happening here. You start at Q0, and you can read A, and you are in final state. So you have A is already in the language, right? So you can write that L is A is in the language. Now, but you can go, you can stop here. If you stop here, you have A. Now, you can keep going here. Now, when you look at this loop, what does it mean that you have this situation Q1 B A, and here you give A, and you, of course, you have to start somewhere Q0. So what's happening here, when you first read A, so you have A, and now you can go A or B, so you can go A, B, and you can go any possible ways of combining those A and B, so you have A or B Kleene star. And now there's another important thing, that if you have a situation like that, you have a state which is final in initial, the language of that automata is E, because the transitive closure gives you a computation of the length 0. So you always get here, if initial state is also a finite state, you get also you get E the word E in the language. And here's our theorem that E is in the language of deterministic automata if and only if initial state is also a final state. Because E is in the language, by definition, you need to have a reflexive transitive closure between SE and QE. But this is possible only when the computation is of the length 1. So it means that when SE is SQ, they are the same, S equal Q. So it means when the S is in F. And then we know also, now if S is in F, we know that that is reflexive closure. So SE is always SE when S is in F, so we get E is in LF. So that is very important property of deterministic finite automata. And we have, now you can have, okay, now we have another notion which is very important, that we have a notion on a trap state. And let's look at the previous example. It's nice. You can see at this example that computation always starts here. So you start with Q0 and you go this, so you read A, and then you read all possible things here and you end up. Now, if you go and read B, whatever is happening on this side is not accepted, is not in the language, because this is not a final state. So the state, such is called a trap state. So they, like, sort of everything was here is trapped in the state Q2. So we have the notion of a trap state. Trap state of the finite automata is any of its states that does not influence of the language. And you can see when you have, for example, the diagram, and you can see that if you get here, wherever gets here, this is not a final state. So you need, the delta is always a function, so you have to define what's happening. But that state, whatever is happening here, does not influence the language. And this is also a trap state. So the only really part which defines the language would be so would be only this, you see, that does not influence the language. So the only part which defines the language would be what's happening between Q1 and Q4, which is the end state. So the language would be just B. So in this way, we have also the, why we need the trap states? We need the trap states because the delta has to be a function. So if I define delta on A, I must define delta on B. So whatever is happening on Q0 and B, it doesn't matter. It does not influence the language. So we just, we can throw out the trap states. And so we introduce the notion of a short diagram. So it means you don't write trap states. So here, really, the short diagram is a part of the diagram which defines the language. So here, that the language is defined by that, and then you can have the rest is that state is a trap state. So again, another notion which, like the pictorial language we will be using, that first we have the full automata. Delta is a nicely defined function. Now I can remove this trap state, that without saying trap state is not an automata, because delta on Q0B is not defined. But if I say plus trap states, it means I did define delta on the whole. Delta must be defined on the whole K sigma. The domain of delta is the whole sigma. So if I say trap plus trap states, it means I completed the definition of delta, but it does not influence the language, so that's okay. So that is first thing. And also, we write the names of the states. When you do the diagrams, we write the names when we want to specify all these tables for delta and put. But we might skip the names, because when you want to, if you don't need to specify all the components as was defined, I can see, OK, here I have initial state, I have final state, and I remove the trap states. So that is called a pattern diagram. Whatever you put the names, the language would be A, or B. So you can see for this, the language of this automata would be A concatenated, A, B, and clean star goes. And we can skip the names. It's called a pattern diagram. So we'll be using the pattern diagrams. For example, here is like nice simple automata with nice simple language. When you have a pattern like that, what does it mean? That you have the language of this automata is A or B sigma star. So it's just sigma star. So this is regular expression, and then is just, remember, sigma star is not regular expression, but that is regular expression. So, so that is a nice pattern diagram. You can see better. Here is, you can write that this is the language of this is A concatenated with that M1. So that is A concatenated with N, because I have A here. And you can see in this automata E, because initial state and final state, initial state is in the is also a final state. E is in the language, so this language contains also E. Why we need the trap states? For example, you have a diagram like that, and you write the delta for this. You have delta Q0A is Q1, and delta Q0A, but it's not defined on B. So the trap states the delta should be defined on all K times sigma. So that's why we need the trap states to complete delta to the full function on the domain K times sigma. And you can have many ways of completing it. But all these ways on B would not influence the language of the automata. So that's why this is like the essential part of the definition of the diagram of M. And on the website, I gave you a lot of short questions, and I want you to study. And they are like this type of questions. Like, for example, you have a diagram, and you have to represent which function, write all possible full the definition of M, and look and write the language. For example, here the language would be, you read A, and here you have a loop, so it would be A star is the language, and the automata is well defined. Here you have The language can be very complicated, but you can see there's no dot anywhere, so f is empty, the language is empty. Here is a nice automata. It's a beautiful automata with language is empty because there's no final state, and it's well-defined automata. Sigma is empty. Remember, I say that sigma can be empty, so this is a nice automata. The only thing which must exist to automata be well defined, you have to you need to have initial state. Other pieces can be, and so on. So here, that is a nice automata. For example, oh, looks very complicated, but it's not an automaton. Because what? That is a nice picture. Goes A, this is not deterministic automaton because I didn't specify the initial state. Of course, there's no computation from initial state, so there's not an automaton. And so it's a lot of nice short, they are called short problems, and I want you to study. That is the book problem. For example, you have sigma is 2 to the power 105, a lot, right? And draw the state diagram that language would be A, because they are numbered, 1025, 8025 star. Or give an example of automaton with such a delta. Delta, you have sigma is AB, and you have 3 states, and describe the language. So again, this is a pattern. What does this mean? It means that you have, you read that number, that element of sigma, and then you read a star, so that is plus a lot of trap states. That's why I gave you such a big. All other states, whatever you have 2 to the power, sigma has 2 to the power 105 elements, so we need a trap state for each of them except for that one. So, and so it follows the same pattern diagram, right? So that it follows the pattern diagram, which we had sigma, sigma star. So also, that is not a regular expression. Remember, we use sigma plus for, but it's not like really proper regular expression. The proper regular expression is sigma, sigma star. And then draw the diagram for transition function. For example, in the book, that is the answer. But you can have, yeah, and when you look at the diagram for this transition function, the language would be that W does not contain 3 consecutive B's and Y. And then the example in the book is one of many possible examples we can define delta. And also very pretty, very complicated, you know, looks like very, you see, similar to our book example. The answer is that is not an automaton, because I didn't specify that picture does not have initial states, so it is not an automaton. Here is nice automaton because there is initial state. And now you can remove final states, so you can have empty and so on. So that is, and there's a lot of examples. I'm not going to go. I just want to see hundreds of examples very nicely explained on the website. So I did a lot of nice examples. In this way you can study them, not only invent everything. But of course, if you want to do it try to invent by yourself and then check with the answer. And also, even if your answer is different than the one I gave you, it doesn't mean that your answer is wrong, because there's many ways. Sometimes there's more than one way to define an automaton for the language with certain property. So that is more problems. I just want to, and again, you have like a short problems. You see, all those short problems have certain reason. I created for you those little problems to put your attention into important things. For example, here, it looks like, look, you have initial state, you have final state, everything seems like it's okay, but it isn't. Because, you see, that is a trap state. Here, this automata would never get to the final state. So really, this is a trap state, and the language is empty. And F exists. So you can have an automata which has a final state, for example, here, but the language is empty, because that final state is a trap state. So really, only the part is automata with the language. So there's a reason for each single example, just to make you think for interesting cases, let's put it like that. And there's a lot of other. And some of them are from the book, when it is. And here's, of course, the state diagrams are very nice, because you can like sort of see how the transition function goes. So how which kind of words are accepted by the automata. Okay, so now we have so this was deterministic automata. Deterministic automata, they are deterministic because delta is a function. So state and element of sigma determines exactly one place, one state in a state Q reading sigma. There's exactly one other state, or one state to which the automata would go. So this is deterministic. So now we have a non-deterministic automata. So it means non-determinism is essentially the ability to change states in a way that is only partially determined by the current state and output symbol, or a string of symbols, empty string included. The automaton, as it reads the input string, might choose in each step to go to any of its states. And the choice is not determined by anything in our model, and so is non-deterministic. What does it mean, really? It means that now you have not a function for the transition, but you have a relation. A transition function is a transition relation that in a state K, you can read even the whole word and go to a state. And that is, and if it is a function, it's deterministic, but if it's not a function, it's just a relation. Now, just to remind you that if you have deterministic automata, it means delta is K times sigma into k, this delta is a relation between k times sigma and k is the binary relation. One set is this and returns this. So here, delta is a, you can think about the function, any function between two sets. F is a relation, is a set of pairs between A and B. So the domain here is sigma. So delta is our little deterministic delta is a relation between k sigma and k prime. But this relation is a function. Not all binary relations are functions. So now in non-deterministic, you do a little bit more. It means here you delta in a state Q read one letter and go to Q prime. Now you, n is a function. Now in a state K, you can read a word and go to state K prime. So in state Q, now you can read W and you go to the state Q prime. And if that relation is a function, you would say the delta of Q W equals Q prime. But if it's not a function, it can go to different Q prime. So here also, you can read the whole word. So in particular, W is in sigma star. So in particular, you can read E, because E is a word in sigma star. So now, again, when you look at this, K is finite states, is non-empty, alphabet is the same, can be empty, S is initial, F is the final set of final states, can be empty, and we have in the definition of delta, we can say delta is a finite set. Why we have to say finite set? Because this set is infinite. And we want the transition to be only a finite set. So we say that delta is a finite set because that is, and it's called transition. And delta can be empty, is the same as here delta also could be empty. And this is a case to consider. And now the transition, and that I explained that the delta was also a relation, so that we already talked about it. And so diagram. Now we extend the notion of diagram for non-deterministic. So non-deterministic now, we have M, non-deterministic, M, you have K, you have sigma, you have delta. See, you have S, you have F, and we use small and big delta, that now delta is a relation between K and sigma star goes to K, and finite. And you have, because this is infinite set, you have always say that it's a finite. And we extend the notion of the diagram. You can say Q, W, or Q1, Q2. So what does it mean? Now, if you have, you can write that Q1, W, Q2 is in our delta, because it's a relation, so the trap triple, you cannot say equals because there can be more than one. So that is a triple is in a delta prime. And in particular, W can be E. So for example, you have a little automata now, whereas what's sigma is empty, but E is in sigma. Remember, E is empty, is in empty star. So even if sigma is empty, E is in sigma star, and there is a nice little automata with empty sigma with two states, and the language is E. Now another example, here Q reading A goes to Q1, and Q reading A goes to Q2, and is not deterministic because looks like deterministic, doesn't it? But it isn't deterministic because in a state Q, you can read A go to 1, so you have this tuple, and Q reading A, you can go to Q2, so that delta is not a function. So delta is a relation which is not a function. So, and the language would be just say. And again, you can see, is it deterministic or non-deterministic? First of all, that's already, if you see E, whatever happens, you know it's not deterministic because you cannot, E is not in sigma, so you cannot have E, you cannot read E in non-deterministic automata. Again, this is another example. Here's very nice. You read E, oh, you know that's not deterministic. Also, you know that's not deterministic because here reads the word, and in deterministic, you can only read elements of sigma. So, so it's not deterministic, and of course, F is empty, so the language is empty. Now, we have another definition, which is a book definition. I let you, and I call it the lecture definition, I let you read delta lecture. And I will explain you why. It's very, delta, I say, is K sigma star K. So it means that is okay. Going from one state, you can read W in sigma star. You can read W in sigma star. In the book definition, and you say also that this is finite because this is infinite set. In the book definition, delta is K times sigma union E K. So what is the difference is that you can, here between two states, you can read sigma, or you can also, on the diagram, you can read E. So this is like sigma in sigma. But you can also read E. And you don't need in the book say that we said that this is a finite state. You don't need to say that is finite because this set is always finite, right? Because sigma is finite plus one element. So it's just, so for example, this is a non-deterministic. You read E, and then you can see the structure. And it follows book definition. Of course, the book definition is a particular case of our definition because this is a subset of. And now we can it is. I will show you how to transform our book definition, lecture definition into the book definition. But it's very comfortable to have automata which could read, for example, let's say, I will draw you a picture. A, B, okay, here is your diagram, which is the language of that automata. It's good because you have initial state. This is your final state. And so what would be the language? Would be you can read A, B, and you can stop. You are here. Or you can read A, B, and go into this loop would be A, B, C, star. And star, it's empty, is included in this, so you can have one time, oh, ABC, okay, sorry, ABC, right? So sigma is for the change A, B, C, and the language is given by such expression. Now, so it's nice to read chunks. If you wanted to write the same, transform that automata into the book definition, what it says that you cannot read two. So you can transform into I am here, and now I can read A, and I add, let's put this is S, and this is Q, all right? So I am in S, I read A, and I put a new state. I add the state, and from A, I add another state, P, B, okay, and now, so I split this by the state. Instead of reading that chunk, I read A, and I add a new state, and now I read B, and now here I am in state Q, and I cannot read 3, so I can read A and add the state P2, and then I can read B and add the state P3, and now I have to go back to, so go back to reading C. So you can see that that is, this automata has the same language. It's just much more convenient to read chunks instead of going like this. And that is, we can, for any automata of the lecture definition, you can add new states. So this automata would have our K would be, you add S, and you had Q of our initial automata, and you add new states P1, P2, P3. You added 3 states, so So you have exactly the same language, but it's convenient to be able to read in chunks. Why we have two definitions? It is because our goal is to prove relationship between automata and regular languages. And we will use non-deterministic automata to do so, and then transform deterministic, non-deterministic automata into the deterministic automata, and then it would be those. To prove the main theorem, it's easier to have that definition. So, equivalence of automata, because I just said that we will show that non-deterministic automata is equivalent to deterministic automata, and that would be our one of main theorems which I am going to prove. So we say that two automata are equivalent if and only if they accept the same languages. So I can see this was my language M1, and that was automata M2, and here you can see from that M1 is equivalent to M2 because obviously they accept the same language. So you can transform one automata into the other. So, and now we have equivalency statement. The notion of a deterministic and non-deterministic automata are equivalent. So we have two equivalence theorems. Equivalence theorem 1, for any deterministic automata, there is non-deterministic, that this is equivalent. It means that they have the same languages, and for any non-deterministic, there is a deterministic such that they're equivalent. So that's why we prove those two theorems or equivalent statement. We can choose, because you can see you have equivalent, you have deterministic automata, you can always have non-deterministic and vice versa. So we will be talking about finite automata, which means deterministic or non-deterministic, because we know that they are equivalent. And this is our goal, to prove the equivalence theorem. So first, equivalence theorem 1, deterministic is non-deterministic, is of course because it's a particular case. So the equivalence of non-deterministic, that for any non-deterministic automata there is a deterministic M prime which are equivalent, it means have the same languages. This is not a trivial proof, and we have a constructive proof. We will we'll describe a given non-deterministic, a general method of construction, step by step, a deterministic automata that accepts the same language. So, but before, and it's a beautiful construction. So I want to give you some idea why the construction is carried this way or not the other. So here is a lot of examples and questions, so I'm just leaving you for, that's all on the website. So they are, you know, the website has really a lot of beautiful examples. So, and on my lectures, I just want to show you, oh, look, you have this example, you have solutions. So it teaches you how to construct more and more automata, or go into details in certain proofs, etc. So there's another problem before we get into that proof of equivalency of automata, that the equivalence of two book definitions, right? That our definition and the book definition, when you can read only a letter and we can read the word, so that is really example of that you have our definition and you transform into the book definition. And how you do it, you stretch it. So the technique is a stretching. In our definition, I read the word, and here I stretch it. This word A, B, I stretch into reading only elements of sigma by added new states. So this is just a stretching technique, and general technique is like this. If you have a diagram delta, what you do, you add, if you want, you add, for sigma 1, you add a new state. For sigma 2, you add the second. For sigma n minus 1, you add another state. So you add new states, and the same when you do if you have from Q to Q1, you add your states. So you always, if you read a word, you can always stretch it by adding new states. So that is a general description of that example. So really, you can do this is called a stretching. And you can construct the new one, and it's a nice nice general description. If you want have a general way, you go to you can. This is proved by how this stretching works, and then here is a nice general description how the stretching looks with, you see, delta sigma would be this, and how to describe it nicely in general case. So now we need this stretching for the proof of equivalence. So we want to prove now that we prove that for any non-deterministic, there's deterministic, that languages are the same. And now I want to, okay, I will show you an example. What is the difference? The difference between delta, small delta, and big delta, right? Small delta reads only sigma, and now the big delta, and I use the book definition because I can assume that now delta, I stretched my automata with reading sigma star, I stretched to the definition sigma union E, right? So I can always have this stretch technique to have delta in the book definition. So so now I assume that I use only book definition. If you use the lecture definition, you stretch it and you have book definition. So now let's look how those two delta, which is the difference. The difference is, first here, sigma is sigma, that you can read E. So this is one, that here you cannot read E, and here you can read empty word. And this delta is not a function. So let's now first look, what does it mean that this is a function and this is not function? So not function. Let's do an example. That you have automata like this. And it looks very similar. There's no E. So let's see. But you can see here that in a state Q1, you can go two ways. And remember, you have a mapping between two sets, and it's not a function if you have A can be mapped to A1, A2, right? So it's not a function. So here, Q1, you can map B goes to Q2 and Q2, so our delta is not a function. And this is your situation. In a state Q1, you read B, you go to two different elements. So that is not a function, right? From one, you can go reading the same into two different. So how to transform it into a function? Because the transformation non-deterministic case into deterministic, I want the case. So simple idea. I want delta of, first, idea is that you have the situation Q1, Q2, Q0. Read the same, so it's not a function, or whatever I wanted. But first, I want, if I put that our states are now set of states, and I read B and go to Q1 to another set. So that is a function. I have one element reading B, and this is your another. So now the sets K, I transform a set into one element, and I have our K are subsets of K, of initial K. So now, in our new automata, you have, this is your state, read B, go to another, only one state, which has all those two states together. So the first idea is make states subsets made out of the states of our original. So this state would become one element state, and these two you put together, and now you have a function. That automata would read B and go to only one state, and you can put capital letter Q, and here's capital letter Q prime. This is your Q prime, and this is your Q, so that is a nice function for this state. Reading B goes into only one state. So that was the idea. So now, if you want to see at this situation, if you put delta of, this is deterministic, of Q0 A goes to Q1, is only one state, so one element state into one element state. Delta of Q2 A is only one element, and delta of, that was the one which was bad, of Q1, if you replace those states by element, would be reading B goes to Q1, Q0 and Q1. And also, in this situation, you make what would be initial state. Q0 was initial state of our automata, so the set of Q0 would be initial state of our new automata. And the same, the final state, you can see that Q2 was a final state, but Q2 is here, so that state, because it includes the final state of original automata, would be also a final state. So the idea is you can write a diagram in our new automata. That is your initial state, because now our states are subsets of states, and from reading A goes to one state as before, but reading B would go to those to that set of two, and this set would be a final state because Q2 was a final state. And that would be, this set would be an initial state because that Q0 was initial. And you have plenty of trap states, because here you have two states as 2 to the power 2 of possible subsets of states. So idea 1, we take as the set K prime of set of M prime, set of all subset of the initial, and we need the initial state would be the set made out of the initial state, and the set of states of our M prime would be the set of all subsets, because now our sets are a set of subsets, and now our delta, a function, that's why we use the small letter, would be the set of all subsets. So set of all subsets, because it has to be, there's a lot of trap states. So you have a subset, and you read only one letter, and you assign exactly one subset, because if you have those non-function, then you put them all together. So that's why our M. So in this case, when you look at this, you can say, okay, now I know that they are all sets, so I can rewrite it like this. This is our new state. Reading A, go to another state, exactly one. Reading B to another. So you have a normal automata, and the rest would be a trap states. So the idea 2, so that was first idea. The idea 2 is that what to do with E. That you are in our non-deterministic, from one state you can read E and go to another state and then go. And here you can see that the language of this automata would be A, right? Because you read nothing, and then you read A, and this is a final state, so the language would be A. And the same, that situation, right? You can read A, and then you read nothing, you go to the final state, so it's the same language. So how to get rid of this A? So the E, really, reading E, so you look that we can go like here from Q2 to Q3 without reading any input. So the whole notion is that we have to gather together somehow those states that we can go from one to the other without reading any input. So the idea 2 is a move of M prime on reading on input symbol imitates the move of N on the symbol, possibly followed by any number of E moves. And so we have a definition of EQ. So that is very important definition. EQ is the set of all P that you can go from Q to P without reading. This is a computation. So that is, you go from Q to P without reading any input. And of course, for any state, Q is in EQ because you have always the path, trivial path of length 1. So you always have this. And NEQ is a closure of the set Q under the relation PR. PR, there is a transition PER. So you read nothing between PR. And you can compute how you compute all those EQs. So for example, here, that E of Q0, remember, Q0 is always, Q is always in EQ. So E Q0 would be Q0, you read nothing, you have Q1. And E of Q1 is Q1, and because there's, and Q2 is Q2. So this is your, so given a non-deterministic, we define deterministic automaton as follows. And that is a little bit complicated, but the new states are the set of all subsets, because you could see that to get rid of this function. And the finite initial is the set, because now the sets are subsets of original M. F is subsets of Q, subsets that are intersection with original F is non-empty. Like if you have the final, if you have a lot and one was final, so now your whole set where you had non-function, the whole set is also final. And delta is a little bit complicated, that because delta goes between the set into the set, and this is union EP, such that P is in K, EP, where you can go from Q to P reading sigma for some Q in that Q. So, and we, to find the deterministic, first you have stages. You evaluate EQ, evaluate initial states, evaluate final states, and you have an algorithm how to evaluate delta prime. And of course, the domain is 2 to the power k, so it's very large. So we evaluate delta prime only on states that are relevant to the operation of M. It means relevant, you start from the initial and you go to the next, you go to the next. You don't evaluate all 2 to the, all the states, which is 2 to the power k. So you only relevant, and then you make all others just trap states and forget about it. And it means we, and then we do it in such a way that the language, because you are relevant, because you want finally to, the languages are those which get you to the final states. So you just look step by step, and then you finish reading, and then you see if you are in final state or not. So for example, here is your little diagram, and doesn't have E transitions. So your EQs are just one element sets. And general procedure, we evaluate delta Q sigma for relevant Qs. So you evaluate from S delta prime on S prime, and you look at all states directly reachable from the initial state, and evaluate delta on states which results from the state 1 and reachable from using that formula. So evaluate here, you have delta Q0A and delta Q0B. We look for the transition because in the definition you have the transitions which Q0A to Q1, and we get that delta Q0A EQ1, and EQ1, you see this Q1 was just Q0. And there's no transition Q0B to P for any P in K, so we put the empty, because there is no is empty. And so step 2, we evaluate states which results from step 1. So now you have, when you look at the diagram, you have Q1B, Q2, Q1B, Q0 on the original diagram. So delta of our Q would be P such that Q goes to P delta. So that would be E Q2, E Q0, so it would be Q0, Q0, Q2. And we just keep going. And so you have diagram of the finishing stage 1 and steps 1, 2 of the stage 2 looks like that. And there is a lot of, if there's no delta in between, you put the empty set. And of course, you have plenty of trap states. And here is the diagram of relevant part of M prime. And of course, you see, and plus hundreds of trap states. So now you have a short pattern diagram, because now you can see how it looks like. This is how you computed all the states. This means this is a final state. You see, so this is a dot now is the state which has those 2 states inside. So the final diagram, pattern diagram, would be in initial states. You read A, you go to another, you read B, you go to another. So this is your initial state. And here's the book example, which we worked out very carefully. So it's nice. And it's more, and it's a book calculations. And okay, of course we did 2. You can have more. So this is how the things work. And so we have equivalency theorem that for any deterministic, there is non-deterministic, but the language are the same, and is M prime is deterministic directly from the definition, because of that formula defines a function which is from Q to the Q in 2 to the power K and sigma and all these trap states. And now it's pretty obvious that if you have, this is your automata, if and only if EQW in a new automata, PE, where P for some P in the big P. And we carry the proof of lemma on the induction on the length of W, and everything goes very smoothly. So we have, and we prove by prove that for any W in any states that holds. So the proof now continues like it just carries as it goes. So now we prove that non-deterministic and deterministic are equivalent. One is subset of the other, and for any non-deterministic, we show the construction of deterministic. So now we have equivalence theorem, and we talk about finite automata, and it means construct a finite automata, or we talk about finite automata, you have a choice to construct one or the other. And so when we talk about finite automata. When we talk, we don't want to specify if it is deterministic or non-deterministic. Okay, so now the next part is finite automata and regular expressions. So we now are going to connect finite automata, deterministic or non-deterministic, with regular expressions. And then we will talk about languages that are not regular. So chapter 2, still, slide set 2, finite automata and regular expressions. So now we have a main theorem. So really, we did everything up to now to give a nice proof of the main theorem. A language is regular if and only if it's accepted by a finite automaton. So it means that regular if and only if there is a finite automaton which can be deterministic or non-deterministic, such that the language L is the language of that automaton. So we use, first we prove what's called closure theorem, and that would help us to construct that automaton we need to have. That class of languages accepted by the finite automata, FA, is closed on the union, concatenation, clean star, complementation, and intersection. If you remember that regular languages were closed after union, concatenation, clean star, and so on. So that's why now we sort of repeat the definition, in a sense, of regular languages in the properties of automatas. So remember that languages are sets. So all normal operational sets defined for any languages over sigma are available. And also we defined a language-specific operation. It means clean star and concatenation. So now we want to prove that the class of languages accepted by finite automata is closed under the union. So what does it mean? That we have two automata, M1 and M2, and I want to construct a new one, M, such that the language M is the union of those languages of those two automata. And this is a picture. So this is a schema how you do. It means you have one automaton, M1, which has initial states, some final states, and things are happening. And then you have another one, M2, which has finite sets, initial states, and all things are happening. And I want to construct M, which would accept the union of languages. What does it mean? I take a new initial state, S of that M, and I go reading E to the first automaton, to S1 of the first, and reading E, go to the second. So the language accepted by that automaton would be the union of two languages. And now what's happening, that internal set, initial state of the first and the second automata become internal state, and the final state of M would be the union of the final states of two, and that is how you describe it. Of course, the delta would be the union one delta and the second delta. So that's everything which first automaton does, and the second automaton, and then initial state is a new initial state. It's a new state. And it becomes initial state of S, and you go reading E to the first automata, reading E to the second, and of course F is the union. So this is the proper definition. And of course, when you say what does it mean WS, there is there is Q such that Q is in the union, and now you can use the distribution of quantifiers over this junction and so on, and you can formally prove that W is in the union of languages, what we sort of visually can see obviously here. So you have a visual idea how you do, and here you have, as we should have, a proper formal proof by the definition of W in L. So, and this is an example. You have two automata. So you have one automaton, the second, and the union, the automaton, which is the union. You have a new state, and you go here, and you repeat, and here's the nice. And that's another example. And also you can write the schema diagrams. When you have, when you draw the pictures, you don't need, remember you put the names of the states if you want to specify all the components, but if not, you use the schema of automaton like here. So, so now concatenation. The class of languages accepted by finite automata is closed by the concatenation. So how you concatenate? So here you have M1. Here's M1 doing everything and M2 doing everything, and you want to concatenate. Again, idea is very simple. Our M is the whole picture. So the initial state of the first, because concatenation, you do everything what M1 accepts, followed by everything which M2 accepts. So this is everything M1 accepts, and you follow by everything. So what you do, you take everything which accepts, and from final states of the first, when you finish, you go to the initial state of the second, and of course those final states becomes non-final states in M, and this you see S2 initial becomes internal state, and the final are the final of the second. And here is the proper description, and an example is, remember that you have one, you have second, so you have one, and you go from the first automata, you read E, you go to the second, and you must read E, and then this are becoming internal, and the rest is, so it's very, and there's, now, for example, if you want a language, and you want to construct an automata for that language, you can split that. This is a concatenation of pieces. So you can construct automata for each piece. For example, M1 would be AB. So here is M1, right? AB, very simple automata. And now M2 would be A star. So this is A star. And M3, where it is, M3 is here. M3 is B star, so it's like A star. And then you put the concatenation, you put it together like this. You see M1, you go E to M2, and so on, and you have the language, and you can split it in all possible. So see, it gets you already, you can build a finite automata for more complex language using already the pieces, you know how to combine them. For example, here combination is by concatenation. So, and then I discussed that you really need to put E in between. So, for example, this is an example why, when you do the concatenation, why you need to split into E. So, for example, when you have those two automata, and you do E, this is a correct answer. If you don't do it, you have that if you would just put them together, you would not get a proper you will not get the proper language. For example, if you put it together, you get such an automata. See, here the correct is that you separate them by E. Now, I said, oh, why always to separate by E? Because if you don't, that automata would look like that, and you have that A, B, B, A, B, A, B is in in M prime, but it's not in the proper language. So that is an example that you do need have those, not because I said, but that E in between. Sometimes you can glue them together without E. But general construction is that you always have to put E, because in some cases when you glue together, it's not a correct construction. Closure on the Kleene star is a little bit complex. It's not that much complex. So what you do, here's your automata, and Kleene star, what you do, of course, Kleene star, you would go from final to the initial, but you need to have a new state, which is initial state here, and you go, the original initial is internal, so you do the loop which you normally would do, but you need to have that state, initial state, into which you go into that loop, and also that new initial state must be a final state. And here also, and here's the definition, and it's exactly the same. I copied from the picture with the book. And so again, a question is, can't I skip that new initial state? So can't I just go back? And this is the answer that you can't. So, and if you do it, you don't get what you need. So you must have that. And of course, you must have, in the case with F1 is empty, original is empty, so the language would be empty, but the Kleene star of empty language is E. So that's why you must have that, new initial state must be a final state to get that, E out of the automata with the language which was empty. And why can't we skip introduction of new initial state? Because again, if you do like this, you will get, you see, if you do like this, you will get AB is in LM, but AB is not in LM plus star. So that justifies the correction of the construction. You always need to justify the correction. So, and the correct construction would be this. And then you can play, you have this, you have a more complex, you can see here I can construct the union, here I can construct concatenation, and then I construct the Kleene star. So for example, here I just split it in pieces, and then I construct the union, and then from the union I construct, you see, the new S and go E, and from the final go here, and I have the construction. And then there's another example. So it's a lot of examples. So we proved that union, concatenation, Kleene star, complementation, and intersection. So complementation is here. You see the automata we did here, they could be finite. It means can be deterministic, non-deterministic. For the complementation, I choose the deterministic. If I have non-deterministic, I go through converting non-deterministic into deterministic with all these states which are sets of states and so on. Very big construction, but we can do it, and it's algorithmic. And so I can assume that I have deterministic, and of course complementary language sigma minus L is accepted as deterministic, identical with M except for final and non-final state are exchanged, so you have a closure at the complementation for intersection. This is one of very mathematical proofs that we know that intersection of two languages is, by the Morgan law, sigma star union complementation of by the Morgan law. This is complementation of L1, union complementation of L2, and complementation you get intersection. It means, to make it A, B, sets complementation is complementation of A, union complementation of B, and of course the complementation of A is minus A, so this is sigma. So by the Morgan law, so I need and I want, so the intersection of two sets is equal complementation of A union complementation of B. So that is the formula. And of course, we have that I have language M1, language M2, and I construct the intersection of automata LM, which is the accepts the intersection of two languages, first transform into equivalent deterministic. Big job, but you can do it, right? Then you construct the complementation of those deterministics, and then you construct the union and transform non-deterministic again, because that might be non-deterministic, into deterministic, and then you take this. Because you see this, when you take union, you have E. So again, you got non-deterministic. So again, you transform it into equivalent deterministic, and then you have, so it's end of construction. So that's rabbits out of the hat, but it's a lot of construction. Everything is constructive. So it's not really very direct, right? But we can do all this. So we prove the intersection, so we prove the closure. But of course, there is deterministic construction of intersection of automata. I write the intersection of automata. It means automata such that the language M is intersection that in a direct way. It means I take that now my M1 and M2 are deterministic, so I only transform them. If they are non-deterministic, I both transform into deterministic, and I construct automata, which the states are Cartesian product of two states. And now S, so S is Cartesian product of S1, S2, and F is the same, and now the delta of the state is the tuple of Q1, Q2. Sigma is this delta does the same which was the first automata doing on the second coordinate what the second automata is doing, and of course W belongs if and only if you go through the coordinates, and so it's a very beautiful and obvious construction. So this is called the direct construction. And of course, the delta you have to, of course, you can also do it for non-deterministic automata. So if you don't want to go through the transforming, if you do the non-deterministic, you can do similar way, a little bit more complex, of course, but you can do it. And and that is a nice example of direct construction. I just wrote you nicely how it looks like, f for the particular case. And the automata would look like that. So we proved that now goal is to prove the theorem, right? So language is regular if and only if is accepted by finite automata. So for any regular language, there is a finite automata, and for any finite automata, the language is regular. So there are two pieces, right? If you have regular language, I will construct the automata, and if you have automata, I will prove for any finite automaton the language is regular. So what is regular language? Just reminder, that was a long time ago, that language is regular if and only if it's defined by a regular expression. And what is regular expression? We define the set of regular expressions as all finite sequences over the finite alphabet that empty is regular expressions. All sigma and sigma are regular expression. And what? Close at the concatenation, union, and Kleene star. So if you have a language, L, there is a finite automata because L is regular if and only if there's a regular expression. So L equal R, and what we do, if regular expression is empty, the language is empty, the diagram of automata, I have an automata. So I called it M empty, right? Now, sigma, the second condition for regular expression, you have M sigma, you have the automata, so that automata, right, which language is sigma. So so we denoted M sigma. And now, by definition 3 of regular expression, we have that R can be union of regular expressions, concatenation, or Kleene star. So what we have, we already constructed M alpha. You construct M for that as the union. You construct as concatenation because we proved that automata are closed under the union, concatenation, and Kleene star. End of the proof. So also it gives us a nice automated method of constructing automata. You don't need to think much because, for example, I have such expression. So I construct M. For sigma has 2 letters, so I construct MA and MB. And now I construct the concatenation. So this is automata MAB. Now automata AAB would be concatenation of those basic 3. And now I have those basic. So I have the union is the union construction. I have this, and I construct the union, and then out of the union I construct the Kleene star. No thinking. So once you know the algorithm of constructions and we prove that that's correct, I know that that automata is correct. It's not the simplest, but you don't need to, you know that is correct, and also you don't need to think too much. So for example, when you have to construct such thing, you construct in stages. You construct the basics. So this is the regular, each sigma is a regular expression. You construct those pieces. So I construct ABC, I construct A star, and I construct A star B. I have A star, so I construct A star B, and I construct the union, and I have this, and you draw the pictures. So, and that's it. So now the inverse is complicated, but not that much. So now we want to prove that if you have an automaton, the language which is accepted is regular expression. So for a given automaton, I give you the algorithm how to find that regular expression. Not like looking at the diagram. No, that's this. It's for any automata. So, and of course, we assume now that proof is constructive. We give an algorithm how recursively generate a regular expression. We assume that we have non-deterministic, and we assume that we use the book definition, because we want these A's, B's, like the smallest pieces. And we prove all, we assume this is important, we assume that we put all the states into one sequence, where S is the first, and final somewhere. And we built the following expressions. Rijk is the set of all words that from the state Qi, reading W, you go to Qj, and you read W prime, where Ijk is the set of words spelled by paths, all possible paths from Qi to Qj in such a way that they do not pass through intermediate state numbered k plus 1 or greater. Now, when you look at this condition, do not pass, so through state numbered k plus 1, do not pass m greater k plus 1, it means m is less than k. So we have the definition of that relation, m can only pass through states numbered m less equal k while going from Qi to Qj. And when you have k equals 0, here 0, so what does it mean? That m goes from Qi to Qj only through the states numbered m less than 0. There's no such states. So means that goes from Qi to Qj directly. So this is very important. So it means that this is all which goes from here to there directly. And we use the book definition because it goes directly. So what does it mean? That goes through Qi to Qj. Means that at this book definition, so it is A in sigma union E because it's a book definition. If I is equal directly is not equal J, is in delta, so you can read it from the diagram. And it is E union A when they are when there is a loop. So you can have, so you really, those Rij 0, you can read from the diagram of original automata. And case equal n means that goes through all states that as k, the number the number of elements in k is n. It means that m will read only w in sigma, so you will get that ijn is qiw goes to qie. But w is in Lm if and only if is in R1, which is initial state, right? Because we put all the states in one sequence, and finish in the final state. So the language would be the union of all 1jn for qi in F. And we prove that all sets are regular, so the Lm is also regular. And we get the inductive formula. Here is inductive formula for Rijk, and then you can compute everything. And you have a lot of examples. You can write a program. That was a long time ago when we had like more relaxed classes because there were not that many students. So we used to give homeworks, and that was a very busy homework. And some more lazy students would write programs and bring beautiful results. Okay, so this whole construction really is reflected in the notion and justified by the notion of generalized automaton. And so this sort of, I'm showing you now how to build it without writing computer program with the recursive Rijk, right? So generalized automaton, GM, is a generalization of the non-deterministic automaton. It's a very interesting generalization. So it has only single final state. The sigma is sigma normal plus all regular expressions, where R0 is finite subset of the set of regular expressions. So it can read regular expressions. So it's not like normal automaton. That's why it's called generalized. Transition may be labeled only by symbols in sigma union E, but also by regular expressions. And the delta G is, you see now, is in a state you can label by sigma or regular expression. And there is no transition going from initial state out of the final state. And if QUP is in, so it means if QUP is in our transition, it means it's not initial state and Q is not a final state. And now we have a method of construction and regular expression such that language of M is that regular expression by the use of that generalized automaton. So here's a picture. You have your automaton, and normal, and this is M, and you put a new initial state, and you go to old initial state, and you go to E, going to the new final state. So these are normal final states. And states are numbered. So you have S is Qn minus 1, and F is Qn. So you have to renumber all the states. So we rename the states that SQ is Qn minus 1, so that's the only thing to remember. And F is Qn, and delta is, as I said, is Qn. This goes from new initial state to the old, and from any final state to a new final state. And of course, the language would be the same because nothing was added. And now we construct the sequence of generalized automata, which are equivalent, and where the last one, n minus 1, have only 2 states and 1 transition, and such that the language would be that R. And how we do it, here's the fragment. If you have state Qi and Qj, which reads delta, and Q, here you have expression alpha. And here, you see, you go expression beta, we transform this situation in generalized automata, because these are regular expression, that you go from qi, qe, you read delta or alpha, beta, right? Concatenation alpha, beta, you eliminate q. So that is, we eliminate, we have all those states, and the method is by elimination of all the states between initial and find the new initial and final. So here q has been eliminated, and of course the new one, g prime, is equivalent to gm. And now what's happening when you have situation like this? Here you have a loop. So to eliminate this q, you would have delta, you have alpha, here is delta sigma star and beta, and you eliminate that q. And then you eliminate everything, and at the end, that's how you construct. You see, you construct this new by this elimination. You construct the new what this automata does. You construct the regular expressions. So let's make an example. Here's your small automata, and now generalize. You keep this. You rename the state. So that would be, this is was q1, q2, q3. That would be q5. You add, right? So this is n minus 1, and this is n. And now you eliminate. So you want to eliminate q1. So so to get to q1 from q4, if you eliminate q1, you go a star and b, and now that part has to be attached here. So if you eliminate this q1, you have to add also this part. So from here to there, you read a star b, but this b goes here. So you b, but to get this b here, you have to read what it did. It would be b a star and b. So you have the expression here, b a star b. And so we have that, and now I want to eliminate q2. So what it would be, this is a loop, so would be, you have a star b, here you have a star, because you eliminate this, you have b a star b, you have b, you have b a star, and then you have b a star b, and that whole thing becomes that loop here. So you have the expression here, and now you have to eliminate that part, which would be a b, and you have concatenation with the whole, and so that's the language. So it's very beautiful. And there's another example which you eliminate both. And again, it is here, this part, you see, this is this loop, and this is similar on that side. So you have this, and so now to go from here to there, you eliminate this, which you would get. You see, that would be this or that, and clean star. So that's the language. So now, languages that are not regular. First, we know that there are countably many. It means continuum languages over alphabet. We also know that there is Aleph 0 regular languages, countably many, so that we have that there's continuum as many as real numbers languages that are not regular. So there's plenty of languages, more than we wish to have, that are regular. And a reminder, regular is what's defined by regular expression. So, for example, and they are different. This is regular, nice, because this is a regular expression, so this regular language. But the language an, bn, and greater than 0, which is a subset of this language, is not regular. So regular language can have a subset which is not regular, and that is, we are going to prove it using a very important lemma or theorem, which is called pumping lemma. But in a sense, when you want to think that cannot be regular, because here you have to sort of compare. Here's any number of A and B's, but here you have to compare, to read n and remember how many n's you read when you start to read B's. So you need to have certain comparison. And that would be another type of automata, which would be push-down automata, which would have certain memory, that you read A and you somehow remember how many A's you had, and then you compare, you read B and you compare with what you already read. So that is much stronger automata, and that would be our next subject, push-down automata, for next chapter. So can be regular, we can't construct, and I said that we would need this comparison and so on. So we will, chapter 3 will study those new type of automata, which are called push-down automata, and together with them we will study a new larger class of languages, which are called context-free languages. And we, of course, we will prove also the main theorem would be that the class of this new class of languages, context-free languages, is the same as the class of languages accepted by push-down automata. So we have regular languages and finite automata. They are equivalent in this sense, and then we'll study a new type of languages, which is called context-free languages, and new type of more general automata, which are push-down automata, and prove the similar equivalency theorem. And then, for example, this is regular, this is regular, this is a good example, an, but it's just n, so it's the same. But you have an, n is prime, is not regular, because how to find that n is prime, so that's another story. And even is regular because you have expression. So you see some property, that property defines, because it's AA, so that language is even. AB such that have equal number of A's and B's. That's not trivial. And this is a nice proof. Assume that's regular. So let's consider that A star B is regular, but our language is the intersection of, takes the language which is intersection, which has equal numbers A and B with the regular, and we know that the class of regular languages is close at the intersection, so you would get the language this intersects with that gives A and Bn, because it's the same number of A's and B's. So it's not regular contradiction, that is not regular. Now, there is WW reverse is not regular, and we use pumping lemma to prove it. WW is not regular. we use pumping lemma. The language xy, x in L, y not in L, is for any regular L is regular, because that can be replaces concatenation of the language and complement of the language, which we prove by closure theorem. This is regular, the concatenation is regular. The language WR, where are the inverse words of a regular language, is regular. So it's called reverse language. So for any regular language, the reverse language is also regular, and so on. And here is how you do it. Nice picture. The diagram of the M reverse to the, you reverse delta, and you reverse the whole process, so that's a nice one. Finite language is regular. You have union of finite words, so you can build the automata. The language X, Y, R reverse is regular, which is pretty nice proof, and show that the class of regular languages is not close with the respect of subset relation. So it means given, and also given two languages, is the intersection regular language, is the intersection of two regular languages also a regular language? And there are different answers. So, so these are very nice questions about, for example, given two languages such that intersection is regular, does it imply that both must be regular? And the answer is no, because if you take two languages, we know that that is not regular, that is not regular, intersection is empty language, beautiful regular language. This is very also nice. X, Y, X reverse for X, Y in sigma is regular for any sigma. Nice exercise. Given a regular language, show that the language X, Y, that X in L and Y not, is also regular. Nice. And then I put some review questions. Also, yeah, just for you to have with the answers. So I do a lot of lectures, and I have special lectures on the website with a lot of review questions, of review of the chapter and so on, so to give you ways of study what we already covered. So, so I just want to tell you, here they are, and they are on the website for you to study. Now, pumping lemma. So that is, you see, pumping lemma is a very powerful method of at least trying to prove that language is not regular. So pumping lemma is one of general class of theorems called pumping theorems. They are called pumping theorems because they assert that existence of certain points in certain strings where a substring can be repeated or repeatedly inserted. And those inserting is called pumping without affecting the acceptability of the string. And okay, I give you like few of them. I start with one which was in the old book. The new book, which has a more general form. So I decided to go through, to start with less general form because it's more comprehensible, and discuss how you, and prove this one. And the other one too. So the Pumpy-Kleda says that if you have infinite regular language, then there are strings x, y, z such that y is non-empty, and such, you see, that you can pump this y. You see, y to the power n, x, y to the power n, z is in the language for all n. So it says that in an infinite language, there is a word which can be written as x, y, z in such a way that y is non-empty, and we can pump, you see, that part any number of times and still have words which are in L. And that's why it's called pumping lemma. Now, we use this pumping lemma as a tool to carry proof that a tool. It doesn't. It's not always, but it's a tool to carry proof that some languages are not regular. And how we do, it means we have a problem. Giving an infinite language, we want to prove that's regular. And here's the procedure. And we assume that we want to prove not regular. So we assume that it is regular, and we want to get a contradiction. So we assume we want to prove not regular. We assume that it's regular. Hence, by pumping lemma, we know, because it's regular and infinite, that there is a word in the language which can be written as x, y, z with y non-empty, where one is being pumped. And we examine this x, y, and z is the fact that it is x, y to the power n, z in L for all n. If we get contradiction, we proved that it's not regular because our assumption that it's regular led to contradiction. So that is our schema, how we try to prove it. And I'll show you. And now this is beautiful proof, very quickly, that L is accepted, regular is accepted by deterministic. And because L is infinite, M accepts some strings of the length greater than number of states, right? And so there is a word which length is greater than n and looks like this. And we have a computation of this word where Q0 is initial state and Qk is a final state. This is final state. But because the length of W, this k, is greater than n, then the length of computation, and M has only n states. So by Pigeonhole Principle, we have some I and j that the sigma I plus 1 to j is non-empty, because I plus 1 I plus 1 is less than j, that drives M from state Qi to Qj. So that string can be removed and insert a repetition by Pigeonhole Principle. So you can remove it and insert as many, and you still, so that would be our split of our word would be the sigma 1 sigma I plus 1 j, because that is the part which two pigeons goes to one hole. And that's the end of the proof. It's a beautiful application. And now you have the computation which accepts, looks like follows. And then you can have a little bit more general, still for infinite regular language. And so now also I wrote you, so you have a statement, right? There is integer for any word of the length greater than n, because we had this, the whole point was that if the length of word was greater than n, so you could have a pigeonhole principle. So there are those splits such that that would be in L for all n. So here is the statement written in nice pseudological way. I did it in purpose because when you look at the generalization of it, you use really that statement. It's all in your head when you use for all exists and so on. So it's nice to see it, how that whole pumping lemma is written exactly like that. So book pumping lemma is stronger version. It means that book pumping lemma said that L can be regular language, not skips the infinite. Then there is integer that for any word and so on is for the length of xy is less than n. So there's like a little bit. And then you do the same proof by like in pumping lemma 1. And then you can write it in very sophisticated form. And why book pumping lemma applies when L also is a finite regular language, because that generalization, you skip this infinite. And here, if you, for example, look at this, a finite language, and you write this condition, holds because there exists n equals 3, that the condition, this condition becomes as follows, and that is a true statement because the statement w greater equal 3 is a false for all words in this language. So by definition, false implies anything is true, so pumping lemma holds. And that is for any finite language, you have the same reasoning. So, and application. I just want to show you that we'll finish. That AM, PM is regular. It is infinite, so we have pumping lemma 1. So it means there is a word which can be rewritten as XYZ, and you have 3 possibilities for that language. And we show that that split in each case, which will lead to contradiction, so we prove that it is not regular. So consider that split XYZ AMBN, and we have cases. Y, because y is non-equal 0, so y consists entirely of a's. So y is sitting here. Now, y, this y can sit here. And the third, that y can have some a's and some b's, right? And we show that in each of those cases, the fact that x, y to the power n z is in L leads to contradiction. And it's very, so let's, case 1, y is sitting here. So it means x, if y sits here, x must be a to the power p. P is greater equal 0 because x can be empty. Y is a to the power q because, well, q is greater than 0 because it sits here, because, and y must be non-empty. And z, the third, this one, would have some a's, but r can be greater equal 0 because it can start only in b, and s greater than 0 because greater than 0 because we must have some b's. And so now let's look at this our condition x, y, and z. You get this part, this is y, is to the power n. So we show that a, so we must have that p plus n q plus r b to the power s is in L. What does it mean in L? And also you have this condition because those PQ had this condition. But what does this mean? That means that this is in L if that number, P plus n, this, P plus nq plus r, is equal this. So let's take the case which exists here. P equals 0, r equals 0, q, s, you get s equals 0. It's contradiction because s must be greater than 0. This is not for all. And contradiction. Now, y consists only b's is similar. X have to have some b's, y has only b's, and z has another b's. And again, you have that p is greater than 0, y must have at least one b, r is greater equal 0. And now if we take our condition, under those conditions, you get that p, r, q, n, s. And if you take the case r equals 0, which is possible, n equals 0, for all n, q greater than 0, you get that p equals 0, which is a contradiction with p equals 0 with p greater than 0. And of course, the other one is just straight contradiction because with y is a, b, x is empty, z is empty, and equal to, you have that a square is in L in contradiction. So, so that is the proof. For the prime, it's just a little bit more complex. That was a nice proof because it's straightforward. You just write what you know where y stands. You just carefully look at those conditions. With prime, you do the same, but you have to show that what you get is a prime number. And you show that it's impossible, and that is a trick. I didn't do it. I found it in a book, right? So if n is such a number, you have such, and that becomes a contradiction with the fact that n is supposed to be prime. I found a division with n factors, so that ends the proof. So beautiful theorem, and we have a lot of exercises how to prove languages, but also once we could see already, once you know certain number of languages which we prove are not prime, and you have all these theorems about how closure of regular languages and so on, you can prove other languages to be not regular by using knowledge about languages which are regular and not regular. So I think we will end this. State minimalization is yet another subject. I'm not going to do it. It's very technical. It's needed because the problem is how to, you have automata with thousands of states, how to find equivalent automata with minimum number of states. And this is when we did the construction of non-deterministic automata from deterministic automata from non-deterministic, we got 2 to the power k states and very complex. So that that was the first question. Can we find equivalent automata with less states or minimum number of states? And that is the whole beautiful subject and nice exercise on equivalence relations. But I will, it's nicely written in on the website. So I will say, so we'll finish at that moment. It's very technical, so it's not too, but it's there for you. Okay, so see you next time.